Hi guys, welcome to this video. In this one I will be walking you through the section A of Exploring Physics paper of June 2022. So let's get right into it. Okay, so in the first question we are given a current is present in the circuit below. The resistor is made from a length of wire. Which row gives the correct charge carriers in the resistor and in the electrolyte? So we know that in resistor it will be the electrons. That would be the charge carriers, and because we have an electrolyte which is basically made of mobile ions or contains mobile ions, the correct option will be B. Now, for question number 2, we are given that the half-life of fluorine 18 isotope is T, okay? And after T equals 4 times the half-life, the number of fluorine 18 nuclei in a source is N. How many fluorine 18 nuclei have decayed in the time interval from 0 to 40? So in 4 half-lives basically, okay? So because after 4 half-lives we were left with N, okay? Or rather, not left with N, the number of fluorine nuclei present were N. You are going to have to start with 16N, okay, at the beginning. And then, you know, after every half-life, so it will be after first half-life or T, it will be 8N. After 2T, it will be 4N. After 3T, it will be just basically 2N. And after 4T, it will be 1N left. Okay, so that means that the number of nuclei that have decayed is going to be 16N minus 1N. So the correct answer will be C. So for question number 3, we are given that the activity of an alpha emitting source is 120 kilobecquerels. The kinetic energy of each alpha particle is 4 million electron volts. What is the rate of energy released by the source? So the rate of energy is essentially joules per second, or simply watts, okay? And we are given over here that the activity of the sample is 120,000 decays per second. Okay, so if you multiply the number of these decay, the activity, okay, of 120,000 by the energy with which, well, they're moving, okay, each alpha particle is moving, is 4 mega electron volts, okay, so if we just times them together, we would end up getting an answer. But they have to be in the right unit, so the mega electron volts must be converted into joules, okay, so we first of all convert it into just electron volts by timesing it by a million, okay, as mega means million, and then 1.6 times 10 to the minus 19, okay, so that will be the amount of energy in joules, and times this by 120,000 decays per second. So that ends up giving us the answer as C. Now, for question number 4, it says, which of the following statements correctly describe radioactive decay? 1. Radioactive decay can be modeled using a dice. Yes. It is random, indeed, and is spontaneous, so all 3 are correct, therefore D is the correct option. For question number 5, we are given that a gamma ray photon of frequency of 6.76 times 10 to the 22 hertz creates a particle and an antiparticle pair. Okay, so where they're talking about pair production here, where basically what tends to happen is you have a photon, okay, and it basically forms a particle, okay, and its corresponding antiparticle. Okay, so it says that the particle-antiparticle pair have 0 kinetic energy. Okay, so that means that they have rest energy. Okay, and we are to calculate the mass of the particle. Okay, so we know that energy is conserved irrespective of whether it's pair production or annihilation. So in this case where you have a photon, okay, the energy of a photon is given to you by HF, and we are given the frequency, which is good. And then the rest mass energy of the particle, of a particle, is simply given to you by, sometimes it's written as E naught, okay, mc squared. Alright, and because there are 2 particles here being produced, you're going to have to put a 2 in front of both of them. And because they are particle-antiparticle, they're going to have the same mass, just the opposite charge. Okay, so if we equate these two, HF equals 2mc squared, we can obtain the mass of the particle by simply dividing by 2c squared. And so when we put in the value of h, which is the Planck constant, okay, and followed by the frequency given to us as that, divided by 2 times by the speed of light in air, so that's squared, and with that calculation I'm going to get A as the answer. Okay, let's move on to question number 6. Now here we are given a potential divider circuit. It says that the battery has an EMF of 9 volts and negligible internal resistance. At room temperature, the potential difference across the thermistor is 4.5 volts, and the temperature of the thermistor is increased, and its resistance decreases by 20% of its previous value. What is the potential difference across the thermistor now? Okay, so we know a very good equation for this. We know that V out, which is the reading on the voltmeter here, is given to you by R2 over R1 plus R2 times by V in, which is 9. Okay, let's say that originally, okay, at room temperature, this was R2 and this is R1, okay, and at room temperature, because the potential difference across the thermistor is 4.5 volts, okay, it is going to be 4.5 volts here as well, which means that the resistance is going to be the same in both of them at room temperature and pressure, okay, just room temperature, okay. So now from here we are further given that the resistance now decreases by 20%. So the resistance of R2, okay, so if I just say R2 dash, the new resistance, is now going to be 0.8 of R2, the older, okay, resistance, the original resistance. So if we just incorporate that into our equation, we would be able to find out what the V out is, okay. So we know that the new R2, so if I just change that around into R2 dash and R2 dash at the bottom, V out is going to be 0.8 R2, R1, or R1 is the same as R2, so that's that, plus R2 dash, which is 0.8 R2, and then times it by 9. Okay, so that will end up cancelling the R2 out as we add them together, and that gives us basically 0.8 times by 9 over 1.8, and the correct answer is therefore B. Okay, for question number 7, we are given a particle is moving at right angles to a uniform magnetic field of the flux density B. The particle has mass m, charge q, moves in a circular arc of radius r in the region of magnetic field. What quantities are required to determine the momentum of this particle? Okay, so we know that momentum is P equals m times v. Now, if you want to look at the overall forces acting on the particles, because it's a circular arc, there will be centripetal force, which will be equal to the force experienced due to the magnetic field, okay, on the charge. So Q is the charge and V is the velocity with which it's moving. So if you just simplify this, we end up getting mv equals bqr. So therefore the momentum, which is this, will depend on b, q and r, which therefore leaves us with A as the answer. Okay, here we have question number 8, where we're given a diagram showing two long current carrying conductors X and Y. They're parallel to each other. Y experiences a force because it is in the magnetic field of X. Which row gives the correct direction of the magnetic field at Y due to X, and the direction of the force experienced by Y due to this field? Okay, so let's talk about X first. Now, in X, we know that according to the right-hand grip rule, okay, which is, just going to try and draw this out with my amazing artistic skills. Oops, gosh, okay. Wow, that is a brilliant hand. Right, anyway, so the fingers are curled and the thumb represents the direction of the current, okay? And the curled fingers represent the direction of the magnetic flux, Okay, so because the current is going up, the direction of the magnetic field is going to be in sort of counterclockwise circles, okay? And you can try that, okay, as well to make sure that you understand it. And therefore we can say that the magnetic field is coming out of the plane of paper. So I'm just going to represent that by a dot, okay, just to represent that that is coming out of the plane of paper. Now, based on that, we know that Fleming's left-hand rule gives us the direction of the force, okay? So if we use the Fleming's left-hand rule, okay, where the first, well, the thumb, okay, I'm going to try to draw this out as well. Okay, wow. Just ignore the rest of the fingers, guys. Okay, so the thumb represents the thrust or the force, okay, and the first finger is the magnetic field, the second finger is the current, and they're all 90 degrees to one another. So if we end up placing our sort of the magnetic field, the first finger, in a way that it's sticking out, okay, so the first finger should be sticking out, the second finger, which is a current, should be going up, okay, so the first finger out, okay, towards you, the second finger up, okay, and the thumb would therefore be facing towards the right, okay, so the force experienced by this wire X will be in, well, towards Y, okay. Now, we know that the force between X and Y is attractive, okay, so that's because the current is going in the same direction in both the wires, the conductors. So it means that the force in Y will be towards X, right? So that will be towards the left-hand side, so it's either C or D. Now, again, if we use Fleming's left-hand rule, okay, we would say that if the force is towards the left and the second finger, which is a current, is towards upwards, okay, going upwards, then we would end up getting the magnetic field direction into the plane of paper. So that basically gives us the answer as C, okay. So do try this yourself, okay, and make sure that it makes sense. If you do have any questions, let me know in the comments so I can go over it properly again if I need to. Let's move on to our next question now. So with question number 9, we are given that a student is investigating the refraction of light by a rectangular glass block. The glass block is surrounded by air, and the diagram shows the path of the light as it enters the block, when it is refracted within the block, and when it exits the block. Which of the statement is correct? The angle theta and phi are the same because the glass block is surrounded by air. Yes, that's right. Why? Because, well, air has the same refractive index, okay? It's air, okay? It's 1, refractive index is 1. So that's why those two lines, those two rays here and here, they will be parallel to one another. In fact, this angle of refraction right here would also be equal to this angle of incidence right here. Anyway, let's move on to our next question. Okay, so in question number 10, we are given a proton of mass 1.67 times 10 to the minus 27 kilos is traveling at a speed of 2 times 10 to the 5 meters per second. And we're given the table below, which shows the mass and speed of 4 different particles. Which particle have the same de Broglie's wavelength as the proton? So de Broglie's wavelength is given to us as lambda equals h over mv. Okay, now because we are given the mass, different masses, okay, and different velocities. Now we don't have to go and end up doing each one of them, okay, because we don't have that kind of time in an exam. So let's look carefully, all right? So if we look at, for example, well, the idea, right, is to have the same momentum, okay, i.e. the same denominator, because h is a constant. So if you have, for example, d, which I can clearly see is double the mass of the proton, okay, the mass of proton is this is, you know, times, this times 2 is d, okay, that number. And similarly, if the mass is doubled, the velocity must half, okay, which in this case, it's working out as well, okay, 1, okay, times 10 to the 5. So if the mass is doubled, the velocity is half, overall, the momentum is going to be the same as the proton. So for that reason, my choice of answer will be D. Okay, let's move on to question number 11 now. we're given a beam of sound of intensity I naught, which is reflected of the surface of water. The amplitude of the reflected sound is a quarter of the amplitude of incident sound. What is the intensity of the reflected sound in terms of I naught? Okay, so we're talking about intensity and amplitude. And at first, this question is a bit meh, there are quite a few, it may seem like confusing at first, but if you just write down A, the relationship between the intensity and the amplitude, and B, how is that amplitude changing? Okay, so we know that I naught is directly proportional to amplitude square. And we are further given that the amplitude of the reflected sound, so I'm going to just call it AR, is equal to a quarter of the amplitude of the incident. Okay, so I'm just going to call it AI, okay, incident sound. So if I just wanted to work out the intensity of the reflected sound, i.e. I'm working out IR, if I just say it like that, okay, just to clarify that this is that, okay, I have to relate this to the amplitude. Okay, so I know that IR over I naught is equal to a quarter AI squared over AI squared. Okay, so basically what it gives me is a 16th of I naught. Okay, some of you might be able to just look at it and know the answer, okay, or guess the answer, okay, and you may have gotten it right, but I always like to use formulae and ratios to figure things out, because I never want to just guess an answer. Okay, so A is the answer for question number 11. So now for question number 12, we are given that a small sample of muscle has volume of 1 centimeters cube and mass of 1.1 grams. The speed of ultrasound in the muscle is 1600 meters per second, and we need to work out the acoustic impedance of the muscle. Okay, so we need to work out Z. Okay, and we are given the formula as density times the speed. Okay, and we are given the speed in the muscle is 1600. So density is mass over volume. Mass is 1.1 times 10 to the minus 3 kilograms divided by the volume, which is 1 times 10 to the minus 6 meters cube. Times it by 1600, and you'll have your answer as C. Okay, let's move on to our next question, number 13. It says that the mass of a proton is MP, the mass of neutron is Mn, the mass of a hydrogen 3 nucleus is M, and the speed of light in a vacuum is C. Which expression is correct for the binding energy of hydrogen 3 nucleus? So in general, binding energy, it has a very similar formula as, well, mc squared, okay, but it's the mass, the change in mass or mass defect, okay, which we are considering over here. So what is binding energy? Well, binding energy is the energy required to keep a nucleus together, okay. So we have in hydrogen nucleus, we have, well, 2 neutrons and 1 proton, okay. So the binding energy will quite simply be the mass of 2 neutrons, which is 2mn, okay, plus the mass of 1 proton, which is mp, minus the mass of the nucleus, which is m, and you times this by c squared, which gives you D as the answer. Okay, let's move on to our second to last question, which says a wire in a circuit obeys Ohm's law. Which statement about the wire is linked to this law? The current in the wire is directly proportional to the potential difference across it. Well, yes, that's right. So let's move on to number 15. An electron has both mass and charge. The electron has a gravitational field and electric field around it. Which statement is not correct? Okay. Both fields look the same. Well, yes, they do. Both field patterns show parallel field lines around the electrons. No, they don't. Okay, so here you have B as the answer. Okay, so basically C and D, they're both correct. Okay, if you think about it, both fields do obey inverse square laws, square law, okay, with respect to the distance, and the direction of the field is the same at any given point around the electron. So B is your answer. So I think that's about it. Yes, that's the end of section A. So In the next video, I will be going through section B questions, which are the long answer questions. And the reason why I split up the paper is because it's long enough already. If I was to do a collective video, it will be super long and you guys would probably not be able to concentrate. So I am just going to leave it here. I will see you guys next week. And yeah, until then, look after yourselves and thanks ever so much for watching.